All right, section 3.6, we're going to look at proving theorems about perpendicular lines. We start off with a piece of vocabulary. It says the distance from a point to a line. So the distance from a point to a line. So we're talking about a line and then a point that's not on that line. The distance from a point to a line is the length of the perpendicular segment from the point to that line. So this piece right here would represent the distance from the point to the line. Okay, this brings us to our first theorem, theorem 3.8, which states if two lines intersect to form a linear pair of congruent angles. So if two lines intersect to form a linear pair of congruent angles, then what does that tell us about line L and line N? It tells us that they have to be perpendicular. If they're a linear pair and they're congruent, they would have to both be 90 degrees. So if they're a linear pair of congruent angles, they would be perpendicular. All right, next theorem, theorem 3.9 states that if two lines are perpendicular, then they intersect to form four right angles. So if we think about what we know about perpendicular, we know that if two lines are perpendicular, they intersect to form a right angle. So this theorem states that there's not only one angle, but there's four right angles. So if we have two lines that are perpendicular, that means that we have one right angle. This theorem is telling us we would not only have one right angle, but we would have four right angles. All right, let's think about how we could just show these angle relationships. If I have one right angle here, I could go vertical to get my other right angle. Right? I could go linear pair postulate to get my other right angle, and I could use those same two ideas to find that fourth right angle. So if two lines are perpendicular, they would intersect to form four right angles. All right, moving on to theorem 310. If two sides of two adjacent acute angles are perpendicular, then the angles are complementary. I think this one's a little wordy, but let's draw that. If we have two adjacent angles and the sides are perpendicular, meaning that this side is perpendicular with this side, what does that tell us about the two angles? It tells us that they're complementary. So if we have this situation where we'll put some points on here, we'll say BA, BC. So given that BA is perpendicular to BC, that tells us that angles 1 and 2 have to be complementary. So again, if two sides of two adjacent acute angles are perpendicular, then the angles are complementary. All right, next up, theorem 3.11, perpendicular transversal theorem. If a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other. So if a transversal is perpendicular to one of the parallel lines, it has to be perpendicular to the other. So we are stating that if, that's some notation here, some symbols here, so we can talk about this. If our transversal, I'll call it line T, is perpendicular to line M, right? If line T is perpendicular to line M, then it has to be perpendicular to the other one. So I'm going to write then line T is also perpendicular to line L. Right? And we can actually prove this using corresponding angles postulate. If I know this is a right angle, then I know up here also has to be a right angle. Okay? Because they would be corresponding angles. But this perpendicular transversal theorem states that if a transversal is perpendicular to one of the parallel lines, it must be perpendicular to the other parallel line. Okay, theorem 312 is very similar to the last one. Lines perpendicular to a transversal theorem. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So in a plane, if two lines are perpendicular to the same line, so I have two lines here, call them line L, line M. We'll say our transversal is T again. So if they are line L and line M are both perpendicular to transversal T, then they must be parallel. All right, how else could we prove this? All right, right now I have two right angles in a corresponding position. So we could use the corresponding angles converse to say that L is perpendicular to M. It's giving us another method to prove parallel lines. So again, in a plane, if two lines are perpendicular to the same line, then they're parallel to each other.